my title is a bit larger than 15 minutes, so I will try to nevertheless convey some message on what the lithosphere structure means for geothermal exploration in rifts. And thanks for posting this nice picture from our section that, however, shows coupled heat and fluid transport of a model in the middle of an intracontinental basin and not in a rift. So I will not show anything of that area. So we are all aware that there were many rifts models developed, and they were developed to explain observed structural settings, the presence or absence of magmatism, and most of them used either or concepts. So we have the active rift, the passive rift, of those pure and simple shear, and we have different wide and narrow rift modes, and depending on the rheological configuration, jelly sandwich, creme brulee, a number of rift models. And more recent work has nicely shown, not only by Evgeny or his students, also almost everyone who's doing geodynamical modeling has meanwhile presented 3D models. And what they all show is that 3D matters, and it's not about either or, it's more about coexistence and continua. But if we go to what a rift will produce in the end, namely a passive margin, there still appears to be very, very strong indications from the observational side that there is a cold and a hot scenario. You can see here the classical distribution of magma rich and magma poor. I will show that using two examples, one the East African rift system and one from the Upper Rhine Graben. And I will show results from models that combine data integration with process modeling. So they are consistent with a number of observations of different kinds, and they are resulting in 3D configurational models on the lithosphere scale that we use as a base for process modeling. So let's start with the East African rift system, the active rift case. We know there is strong volcanism, we know that there is a high topography, and we know that there is a high surface heat flow that correlates with the presumed elevation of the thermal lithosphere-asthenosphere boundary that we can translate from shear wave velocity models that we take from seismic tomography. Here is just one example shown from Schäfer and Lebedev that is crossing the East African rift and shows this big dark blue-red blob below the rift. So how hot is it in this system, and why is it so hot? We look at the sub-area of this system, the Kenia Rift, and that's work done by Judith Zippel, who now is called Judith Bott meanwhile. And I will illustrate that with a few slides that I will repeat also for the other rift system. So we are looking at the depth to the 100-degree isotherm. And what you can see is that this isotherm can vary by several kilometers in vertical position. And we have the highest temperatures basically in this area where this isotherm is shallowest. If we compare this with the configuration of the blanketing shallow sediments and volcanics, we see there is some correlation, but not a one-to-one correlation. And please ignore these reddish colors here. These are passive margin sediments that are not related to the rift. We see, if we look at the upper crustal thickness, that there is a correlation here. And we see the thickest upper crust that is very radiogenic is exactly below these highest temperatures. If we look at the deeper isotherm, the 450-degree isotherm in such a model, we can see that here slowly we start to see the thermal lithosphere-asthenosphere boundary and the impingement of the mantle plume, but still we have this area that is hot, and that is not related to the thermal lithosphere-asthenosphere boundary alone, but it is related to this very thick upper crustal, thick radiogenic upper crust that can be up to 30 kilometers thick here. But we also see, if we look at the configuration, is that we have a thinned lower crust. So this bluish area show areas where the lower crust is almost gone, and the entire crust is composed of radiogenic upper crust. So if we summarize all this, we see in the Kenia Rift that we have a bottom-up process. We have a pronounced lower crustal and lithospheric mantle thinning. And if we want to explore for geothermal energy, we will go for areas where we have the maximum thermal thinning of the lithospheric mantle and the thickest radiogenic upper crust. Sediments are in general thin because the area is so elevated that there is very little deposition. So they are not the key here to find the best places and the thermal blanketing is of minor importance. Now let's move to the Upper Rhine Graben. Here we have a system that is part of the Cenozoic European rift system that evolved on different crustal domains. And again, we would like to see how hot is it at what depth and why. And I will just refer mainly to the results from steady-state conductive heat simulations, because I don't have time enough to go for the coupled heat and fluid part as well. So if we look at the Upper Rhine Graben, we see there is only moderate topography, only the rift shoulders are elevated actually. There's almost no volcanism, apart from the Eifel and the Vogelsberg, there is not much. The surface heat flow is moderately high, and the high values mostly concentrate at places where we have hydrothermal circulation along faults. And if we look at the deeper structure, we see that there is not really a thermal anomaly below. If we zoom in here, so this rectangle shows you the place where the Upper Rhine Graben is located and the model is located. We see that only at large depth we see some sort of upwelling of the asthenospheric mantle, which is in addition offset with respect to the rift location. If we again look now at the same isotherms and the same structural relationships, and we see that the 100-degree isotherm varies quite a lot. So we see two patterns in this map. We see a cold northwestern area where this isotherm is very deep, like more than 3 kilometers deep, and we see a warmer southeastern half, and we see the linear Rhine Graben. And this linear hot anomaly one-to-one correlates with the thickness of the very young Cenozoic sediments. They are poorly consolidated and therefore very insulated, and they are quite thick. These two partitioned pattern of colder northwest and warmer southeast in turn correlates again with the thickness distribution of the upper crust, which has different radiogenic heat production values, because there are different Variscan units that are sutured against each other here. If we go deeper now and look at the 450-degree isotherm, we have lost this short wavelength variation pattern completely, and we are left with only this two-partite northwestern colder area and hotter southeastern area. That again shows a very strong spatial correlation with the upper crustal configuration. And of course, in turn, also with the lower crustal configuration. Means where the area where it is coldest, we have the thickest mafic lower crust, which is producing a lot less heat. And where it is hottest, the crust is almost entirely composed of radiogenic upper crust. The correlation with the thermal LAB is not straightforward and is not evident here. So if we summarize again the situation here, we see that the Upper Rhine Graben is illustrating a top-down process where we have the hottest anomaly in the rift, where we have the thickest sediments, so where thermal blanketing is most pronounced, and where we have the largest radiogenic heat production in the upper crust. The lithosphere, asthenosphere boundary is not so relevant in this case. Of course, in this system, we have a very strong influence of advective and convective heat transport, and I will not have time to illustrate that entirely, but I can say this situation modulates this average general pattern in that we have cold fluids moving along the border faults from the rift shoulders into the basin. They warm up and they rise along the basin axis to produce a general pattern of northward hot rising fluid flow in the center of the Graben. So if I now go back to my initial picture and I compare these two systems and look at what comes out of them maybe afterwards, it makes sense to say that this active-passive rift story may be substantiated also by observations of present-day rifts. Here I put for comparison the Rhine Graben model at the same spatial size as the Kenia Rift, so you have an idea what I'm comparing all the time in reality. So it's a lot smaller, that model.
Eleni, 10 minutes.
Okay, I'm almost through. So that's already my summary slide, and I was hoping that we have more time for discussion. If I would go for geothermal exploration in rifts, I would first of all check what is my lithosphere thickness. because this is controlling my average geothermal gradient. And of course, it's also important to know what type of thinning mechanism do I have? Do I have a bottom-up or a top-down thinning of the crust and lithosphere? Then I would need to check the lithology of the crystalline basement and of the basin fill, because these two components add to the heat budget in terms of radiogenic heat. And in particular, the upper crust adds more than 50% to the total budget of heat in such a system. And of course, the thermal conductivities, chimney effect at the rift shoulders, and insulation in the area of the rift proper with the insulating basin fill is also important. Then, of course, we have heat transport mechanisms. So we may not only have a conductive setting, we may have advection, we may have even density-driven convection. We may have faults that also overprint this general conductive pattern. It's important to know the age of the rift. So if the system is very young, it's probably not appropriate to run any steady state conductive model at all. So one has to consider that, because also sedimentation rate is a question. In addition, sedimentation rate is also a question of steady state or not steady state if the sedimentation rate is very fast. So the system also will not have equilibrated. So caution for these additional mechanisms that I had no time to treat in the talk. And my final conclusion is a very general one. Most present-day rifts are hot at shallow depth, but for very different reasons. Thank you.
Thanks a lot, Leni. We have time for questions. So as I posted in the chat, you're welcome to post your question in the chat, but you can also raise your blue hand, or you just type Q in the chat, and then we know who to give the word. And you should be able to unmute yourself then. So there's a question from Mohammed. Mohammed, would you like to ask the question yourself, or shall I read it out? I can read the question out. So the question is, how useful is the Curie depth estimation as a proxy for background heat flow modeling?
That's a useful proxy, but not if it's the only proxy, because the Curie depth is very different depending on what type of lithology you may have in the crust. If you have a mafic system, that's a different Curie depth than if you have a very felsic crust. So knowing only the Curie depth is not sufficient. Combined version of knowing velocities or densities in the deeper crust and Curie depth is very helpful.
Martin May, would you like to read your question? Okay, so the question.
Yeah, I think I can ask you real quick. Very nice talk, Lena. Thank you. I'm really non-expert here and just interested. So what is a typical temperature range at the LAB? And in particular, if you talk about an elevated LAB and the temperatures there, and how then the heat conducts upwards?
Well, a typical temperature is something between 1330 and 1350. That's actually the place where peridotite in the phase diagram would cut the solidus liquidus line and would start partial melting at a certain pressure, of course, in addition. But it's sort of a 1350 degree house number. And you can translate with different conversion methods, shear wave velocities, for example, to temperatures in the deeper mantle, and try to figure out if this tells you something about your LAB configuration.
There's a question from Cindy Ebbinger. Cindy?
Oh, right. Lenny, thank you so much. I'm imagining that your target, rather than magmatic centers or fractionated magmatic centers with a known shallow heat source, that your target is the large hot water basin systems. Could you comment about deep faults in water circulation and the role of stronger, longer, deeper faults in the two different settings?
Yes, the two different settings have actually quite differently hot faults, and there are also the fluids in the faults are very different. So I probably cannot cover this in a short answer. But what we see in the upper Rhine Graben is what we get along the faults is basically fluids that are heated up according to a more or less normal geothermal gradient with depth. And they find a way to move upward along the fault, so they go there. Whereas in the East African Rift, of course, we have a lot of magmatism, and I have also hydrothermal fluids that are related to this magmatism, which is a completely different origin. So this is different in the two systems, I would say. Very different. Did that answer your question?
Yes, thank you.
Okay, we'll take one last question. It's from Marta, and she says her microphone is not working, so I will read it. And she would like to know, how are the fluid flow trajectories constrained in the Rhine Graben?
That's also a good question. So what we did compare was, first of all, the distribution of artesian wells and the distribution of springs. And what we found was that we get the regional trend is robust, so that we have this general flow field from the rift shoulders towards the basin center, and then according to the slope of the basement, which is slightly tilted northward, it goes along the basin axis slightly northward. So that's robust, but the local resolution, of course, is not fully constrained. And if you really would want to have a model that covers a local exploration site, you would need to zoom into an area and have a higher resolved model. And you need to have constraining data from hydraulic head measurements and time series of hydraulic head measurements.
Perfect. Thanks so much, Leni. And thanks everyone for the questions. I really love that.